Hello, my name is Foram Patel, and I am a fourth-year undergraduate student at Western University pursuing an honors specialization in interdisciplinary medical sciences. I have been working in Dr. Kharche's lab to assist in the development of a mouse atrial cardiomyocyte cell model. My work has contributed towards development of a 3D whole heart mouse electrical model capable of producing realistic neurine ECG. In this workshop presentation, I will be going over digitizing ion channel data of atrial cardiomyocytes using the SCAN software. I will start off by giving some introduction and background information into the clinical significance of collecting this data. Atrial fibrillation is a cardiac arrhythmia that affects various patient groups, including those on dialysis. The heart beats irregularly due to irregular signals propagating from the atria. Electrical signals in the heart propagate from the sinoatrial node, also known as the SA node, which is the pacemaker of the heart, and it keeps it in its natural rhythm. The signals then travel down to the atrioventricular node, also known as the AV node, which is the gatekeeper of the heart, and then down to strong fibers towards the ventricles and throughout the heart. In atrial fibrillation, the SA nodal cells send irregular signals, or there are random impulses from other areas that cause the heart to beat irregularly. In order to develop effective therapies for atrial fibrillation, it is important to understand the electrophysiological mechanisms behind it. Animal models, such as the mouse, are widely used experimental models to study cardiac electrophysiology. The sodium and calcium ion channels play a key role in propagating action potentials during the cardiac cycle. Hence, it is important to study their electrophysiology and collect data that can aid in developing a mathematical model of atrial cardiomyocytes. So what is SCANit? SCANit is a digitizing software that allows to take images of graphs and obtain the displayed data as numerical values. Electrophysiological parameters such as current and voltage data can be obtained using this software to digitize graphs presented in different scientific research papers. The program is user-friendly and allows to obtain numerical data from graphs with accuracy and precision. In the next few slides, I will go over the digitizing steps in order, starting from uploading an image, setting up the axes, selecting points, significant digits, and then exporting the data. I will also go over some special cases and the various other features of the SCANit program that can be used to aid in data collection. Before beginning to digitize the data, we need to save the graphs presented in the scientific papers as image files on the computer. Images can be saved as PNG or JPEG files, either by screenshotting them directly from the scientific papers or by using image extraction programs such as PDF Candy that can be found online for free. Make sure to save all the images with a standardized naming convention that makes it easier to navigate through a group of images later on. Once SCANit is open, the first step to digitizing the data is to upload an image. To do so, open up an image using the drop-down menu at the top. Go to File, then select Open Image. This will open up a window that has all the files from the user computer. Select the desired image and then click Open. This will upload the image on the screen for you to work on. The next step is to set up the X and Y axes. On the top left corner above the image, make sure the mode is set to Set Axes, where arrow A is pointing. And then, using the Zoom View feature panel on the right of the image, carefully select a point on either end of the axes that can be clearly assigned a value based on the graph. Then enter the appropriate X and Y coordinates for that point. For example, in the image shown, arrow B is where the coordinates will be entered, and the blue square is where the selected point is. The coordinate at that point on the y-axis would be -40 for the x and 7.5 for the y. Notice that the selected point is at the small middle marker between the numbers on the graph so that it is 2.5 units away from the adjacent marker. So 2.5 units above 5 would give us 7.5, hence the y coordinate for that point is 7.5. Follow the same steps to enter two more coordinates, one on the x-axis and one where the x and the y-axis intersect. Once that is done, a window will pop up for you to accept axes. The blue box on the right image, where arrow C is pointing, shows the angle between the axes. Make sure that the angle is as close as possible to 90 degrees. If not, then select Cancel, and then go back to the image and adjust the selected points by clicking on them, and double check the coordinate values as well. Once that is done, the window will pop up again, and if your angle is 90 degrees, you can click Accept and move on. Now we can start picking points. First, uncheck the Snap to Nearest option at the top left of the image, where arrow A is pointing. Notice that the mode now says Manual Pick. This allows to manually choose our desired points. For example, this graph presents data about the calcium ion channel current. We only need the control points, which the legend indicates to be represented by solid black squares. As you select points, they will start to appear at the top as pointed by arrow B. Sometimes, the symbols will overlap each other, and that can make it difficult to choose a point. For example, here, the circle overlaps the square where arrow C is pointing. In this case, try to choose the centermost point of the desired symbol. Once all the points are selected, we can modify the number of significant digits for the dataset. In the menu panel at the top, select Data, then go to Format, and then Number of Significant Digits in the drop-down menu. In the new window that pops up, as shown by arrow A, enter the desired number of significant digits for both the X and Y coordinates. Usually, 10 significant digits should give precise numbers of dataset. You should see the dataset values change according to the newly set significant digit value next to arrow B. If you want to delete any points for some reason, such as the wrong point was selected or it does not seem precise enough, then it can be deleted by selecting it from the data set as highlighted in the example over here, and then clicking the Delete Selected Data option. The coordinate will also be highlighted in green on the image where the point is located as shown by arrow A.